Most people treat twosome as a warm-up. I want to show you why it's actually everywhere in production software and why the approach you pick matters. Let's you open Google Maps and you type your destination. In milliseconds, it finds two road segments that add up to your total travel distance. That lookup, it's twosome. Let's break it down completely. If you look at the map, suppose segment A is 2 miles and segment B is 7 miles. Together we get our total destination distance of 9 miles. Alright, the problem. Given an array of integers and a target number, return the indices of two numbers that add up to the target. Let me write this on the notebook so we can see it clearly. Here is our array 2, 7, 11, 15 and the indices are 0, 1, 2, 3 and target is 9. So we need to find which two numbers in this array add up to 9. Look at index 0, the number is 2 and if you look at 1, the number is 7, so 2 plus 7 equal to 9. That's our answer. So we return 0, 1. It's simple to understand. Now let's talk about how to find it, because this is where it gets interesting. The first instinct most people have is check every pair. Pick the first number, check it against every other number. If they add up to the target, done. If not, move to the next number. Let me draw this. I am at index 0. That's the number is 2. Now my inner loop checks 2 plus 7 equal to 9. We found it. But what if they don't match? I would check 2 plus 11 equal to 13. No match. And 2 plus 15? No. And then I'll move to index 1. And I will check for 7 plus 11. 7 plus 11 is and 7 plus 15 and so on. This is called brute force, two nested loops. Here is the code. In line 1, outer loop, we pick every element as a candidate, and line 2, inner loop, start at I plus 1. We never check a pair twice. In line 3, the actual check, do they add up to the target, we'll check that. And line 4, if yes, we return the two indices immediately. The time complexity for this is big of n square because of two nested loops, and the space complexity is big of 1 because no extra memory is used. Now here's where this matters in the real world. Imagine you are a junior developer at an e-commerce company. Your product catalog has 1 million items. A customer wants 2 items that together cost exactly $50. With brute force, you are checking every pair. 1 million items means 50 billion comparisons. Your server doesn't just slow down, your server catches fire. In bioinformatics, researchers actually use brute force on toy datasets, but production genomic systems never. The point is this: brute force works on LeetCode examples. It fails in production. We need smarter approach. Here is the key insight that changes everything. For every number I look at, I don't need to check every other number. I just need to remember what I have already seen. Here is how I think about. If my target is 9 and I am looking at number 2, I don't need to scan the whole array. I just ask, have I seen 7 before? Because 9 minus 2 is 7. That's the complement. Create an empty hash map. Think of it as a table. 2 columns like value and index. And in step 1, I'm at index 0. So the complement is 9 minus 2, that is 7. So we'll be checking does 7 in our map or not. The map is empty, so we store 2 and 0 in the hash map. Now we'll move to step 2, that is index 1, and we'll check complement, that is 9 minus 7 equal to 2, and we'll check in our app the value 2 exists. So we'll be returning 0 1 as our answer. I only looped once, one pass through the array. This is where hash map exists. Big of one lookup. It's not big of n and not big of n square. It's a constant time. Here is the code. In line 1, seen is our hash map. It maps a value to its index. In line 2, we loop through the array using enumerate. This gives us both the index I and the number num at the same time. In line 3, we compute the complement, the number that we need. In line 4, we check the map. This is 0 of 1 instant. If complement is already in scene, we found our pair. In line 5, we return both indices. Scene complement is the earlier index and I is the current. If not found yet, we store the current number and index in the map so a future number can find it. The time complexity is big of n, 1 pass, and the space complexity is big of n. The hash map can hold up to n elements. This is our best solution. This is what you should write in interviews. This is what production code looks like. This exact pattern, I need X, I have seen it before, is everywhere in real systems. First, Google Maps routing. For each road segment, the system looks up the complement distance in a hash map, finds optimal pairs in big of n, not big of n square. In Stripe, the split payments, given a total charge amount, find 2 line items that sum to it. Big of n hash map lookup per transaction, millions of times a day. And React reconciler. When React compare your old and new virtual DOM, it maps node keys to positions using a hash map. Big of one lookup to find matching nodes. That's why React is fast. And in Elasticsearch, the inverted index, which powers every search you ever done, is a hash map. Word maps to document IDs. ToSum is the primitive hiding inside full text search. The next time you search something on Google, you are running ToSum, just with better hardware. Let me put them side by side one more time. Brute force, big of n square time, big of 1 space. It's not production ready. Hash map is big of n time and big of n space. It's a best solution. Both have early exit. We return the moment we find the answer. Hash map is more readable once you understand the pattern, and it scales to billions of records. So, what did we cover today? We started with the institution, Google Maps, real systems. We built brute force, understood it, coded it, and dry ran it. We understood why it fails at scale. Then we built the hash map solution, one pass, big of n time, and we dry ran it step by step on the notebook, and we connected it back to Google Maps, Stripe, React, and Elasticsearch. For interview, answer is hash map and big of n time and big of n space. And what if a senior engineer asks if you have a billion elements and can't fit the hash map in memory? That's your next problem to think about. I will answer that in future video. This is Teja Explains, where we break down complex coding concepts into simple, real-world learning. Hit the subscribe button so you don't miss the next breakdown. I'm Teja and I'll see you in the next one.